We're going to talk about the effects of intermolecular forces. So intermolecular forces impact how strongly molecules will stick to each other, and the main types that we learned about were London dispersion forces, which are the weakest, which are temporary dipoles that result from the imbalance of electron distribution within atoms or molecules. We also have dipole-dipole interactions, which are permanent, partially positive and negative ends, which attract each other. And then we have hydrogen bonding, which is like super-duper dipole-dipole that only exists when you have a hydrogen bonded directly to a fluorine, directly to an oxygen, or directly to a nitrogen. So those are the intermolecular forces, and the stronger collectively they are, the harder it is to do any type of process in which you are trying to separate molecules, which includes quite a few things. So things that it impacts, one, you can talk about viscosity of a liquid. So think about the stronger a liquid is sticking to itself, the harder it is going to be to get it to flow. Viscosity is resistance to flow. So if you think about maple syrup, those are large sugar molecules which have a ton of hydrogen bonding and London dispersion forces holding it all together. It does not flow very easily. Whereas if water is about in the middle, but if you were to pour like butane, there's very small amount of intermolecular forces there relative to the water. Therefore, it will actually flow easier. It also impacts solubility, so things that are polar will dissolve other polar or ionic things, and things that are nonpolar will dissolve in nonpolar things. It impacts boiling point, which is we'll get into that in a little bit more detail after. It impacts capillary action. You've all seen water climb its way up a piece of paper because of its ability to adhere to itself, to be cohesive with itself and climb up, relative to other things that wouldn't do that so well. You have heat of fusion, which is the energy required to convert a solid into a liquid. So you have to overcome the intermolecular forces holding everything in place. For example, to melt ice, you have to overcome the hydrogen bonding there from being in a fixed position to being in a fluid position. And yes, I just threw my marker. All right, and heat of vaporization is the energy required to convert a liquid into a gas. So at that point, you're not just being able to slightly break the intermolecular forces in a way where they're still close together from a potential energy diagram perspective, but you are completely breaking them apart. So overcoming that requires quite a bit more energy. The stronger the molecules are held together, the more energy it takes to vaporize it. So here's just a picture of adhesion versus cohesion. So when we talk about adhesion, we're talking about the attraction of a molecule to the surface of whatever it's on. Okay, water, as we know, forms a meniscus when you put it in a graduated cylinder. And that meniscus is a result of water's greater attraction to the walls of the container versus other water molecules. If you do that with mercury, you'll get the reverse. You'll get an inverted meniscus because the mercury sticks to itself way more strongly than it sticks to the glass walls of the container. It also impacts surface tension. So if you dive into a swimming pool and you do not do it with great technique, you know what a belly flop is, and you know how painful that can be. That pain is a direct result of the force being exerted back on you as you try to break through the water. It takes energy to break it apart. In order to overcome that surface tension, it pushes back pretty strongly. So, and then we mentioned boiling point over there, but let's talk about what boiling point actually is. Boiling point is the temperature at which the vapor pressure of a liquid exceeds the atmospheric pressure pushing on it. So what vapor pressure is the force exerted by molecules at the surface of the liquid, and we have that drawn here in the black as the upward force exerted by the molecules as they're trying to escape. So not only do they have to overcome the intermolecular forces to boil, they also have to overcome the atmospheric pressure pushing on top of that. When it does that, that is when we have reached the boiling point of a substance. Now, how much vapor pressure you have, the higher the intermolecular forces, the lower vapor pressure you have at a given temperature, because they're going to be held together more strongly and they're not going to be free to just kinetically bounce off the atmosphere. So something with a low intermolecular force is going to exert a higher vapor pressure at the same temperature and be more able to evaporate under those conditions. So these are just some of the things that intermolecular forces impact, and I just wanted to give you a brief description of how they're impacted.